There are moments in science that feel triumphant. A discovery confirmed, a theory proven, a breakthrough celebrated. But there are other moments, quieter ones, when the data doesn't behave the way it should. When instruments return numbers that make no sense. When researchers look at each other across a lab bench, not with excitement, but with unease. Science is built on curiosity. But sometimes, curiosity turns into something heavier. A realization that something is off. The world may not be as stable, predictable, or understood as we once believed. Tonight, we're counting down the top 5 moments scientists knew something was wrong. We're starting with number 5. In the early 1980s, atmospheric chemists began noticing subtle but persistent changes in the chemical composition of Earth's upper atmosphere. Ozone levels over Antarctica were dropping dramatically. At first, many assumed it was a calibration error. Instruments fail. Data can be misread. But year after year, the readings showed the same pattern. A thinning of the ozone layer far beyond natural fluctuation. When British Antarctic Survey scientists published their findings in 1985, the implications were staggering. The ozone layer shields Earth from harmful ultraviolet radiation. Without it, life on the surface becomes far more vulnerable. Skin cancer rates would rise. Crops would suffer. Marine ecosystems would destabilize. The realization that human-made chemicals, specifically chlorofluorocarbons, were eating away at a planetary shield was a turning point. It wasn't just an environmental issue. It was proof that industrial activity could alter the atmosphere itself. Scientists didn't panic publicly. They documented. They modeled. They confirmed. But privately, many knew something fundamental had shifted. Humanity had unknowingly damaged a global system designed to protect life. The sky itself was thinning. At number 4, a signal arrived from deep space that no one could immediately explain. In 1977, a radio telescope at Ohio State University detected a powerful burst of radio waves lasting 72 seconds. The signal was so unusual that astronomer Jerry Amon circled it on the printout and wrote a single word in red ink. Wow! The signal came from the direction of the constellation Sagittarius. It was strong, narrow band, and unlike known natural cosmic sources, scientists searched for a terrestrial explanation: interference, satellites, atmospheric distortion. Nothing fit perfectly. The signal was never detected again. What unsettled researchers wasn't just the possibility of extraterrestrial origin. It was the silence that followed. The universe had whispered something precise and deliberate, then went quiet. Decades later, the signal remains unexplained. Scientists are comfortable with uncertainty, but they are less comfortable with anomalies that refuse to repeat. The WOW signal represented a gap, a moment where our instruments picked up something beyond our current understanding, a reminder that the cosmos is vast and that we may not fully grasp what moves through it. At number 3, the numbers coming from climate models began aligning in a way that felt irreversible. By the late 20th century, climate scientists were tracking rising carbon dioxide levels, melting glaciers, and warming oceans. Early predictions had suggested gradual change, but as satellite data improved and long-term measurements accumulated, the trajectory sharpened. Ice cores revealed atmospheric compositions stretching back hundreds of thousands of years. The spike in greenhouse gases during the industrial era was unlike anything in the record. Temperature curves climbed, sea levels rose, extreme weather patterns intensified. There was a moment, quiet, technical, buried in peer-reviewed journals, when scientists realized the models weren't exaggerating. They were accurate, and in some cases, conservative. The unsettling truth wasn't just that the planet was warming. It was that the changes were happening faster than ecosystems could adapt. Coral reefs bleached, Arctic ice retreated, entire habitats shifted northward. For many researchers, the data crossed from theoretical concern to lived reality. The graphs were no longer abstract. They were unfolding in real time. Something wasn't just wrong, it was accelerating. At number 2, the Large Hadron Collider prepared to probe the fundamental structure of matter. When CERN activated the world's most powerful particle accelerator in 2008, the goal was clear: test the standard model of particle physics and search for the elusive Higgs boson. But beneath the excitement lingered unease. Some theoretical discussions, largely speculative, raised the possibility of microscopic black holes or unknown phenomena emerging from high-energy collisions. Most physicists dismissed catastrophic scenarios as mathematically implausible. Still, the idea that humanity was recreating conditions fractions of a second after the Big Bang carried weight. When the Higgs boson was confirmed in 2012, it validated decades of theory. But other results complicated the picture. Certain measurements didn't perfectly align with predictions. Tiny discrepancies hinted at physics beyond the standard model. Scientists thrive on such anomalies. Yet each one signals something profound. Our most trusted framework for understanding reality may be incomplete. The deeper we probe matter, the more we realize how much remains hidden. There's a quiet humility in that realization. The universe obeys laws, but we may only understand fragments of them. Before we move to number 1, pause for a moment. If you're still with this journey through atmosphere, deep space, climate systems, and particle collisions, let us know in the comments. If you enjoy deep, unsettling explorations of moments when certainty cracked and questions grew louder, like this video and subscribe to Deeper 5. This channel exists to explore the edges of understanding where science meets uncertainty. Now, let's move to number 1. At number 1, in early 2020, epidemiologists began tracking unusual pneumonia cases emerging from Wuhan, China. At first, the reports seemed localized. A cluster of infections linked to a market, respiratory symptoms, a novel coronavirus identified. Scientists worldwide began sequencing its genome, comparing it to known pathogens. Within weeks, patterns emerged that were difficult to ignore. Human-to-human transmission was efficient. Asymptomatic spread appeared possible. Case numbers rose exponentially. There is a moment in outbreak modeling when curves stop looking theoretical and start looking inevitable. When transmission rates suggest global spread unless extraordinary measures are taken. For many scientists, that moment arrived in January and February of 2020. The data for Italy, the hospitalizations, the reproduction number calculations, the realization that containment might already be slipping away. What made it especially unsettling was speed. Modern air travel connects continents in hours. A virus no one had immunity to was moving through a fully interconnected world. The pandemic that followed reshaped societies, economies, and daily life. But for researchers watching the early numbers, the dread began before lockdowns, before headlines. It began with data points on a screen, climbing faster than expected. The common thread across all 5 moments is not catastrophe. It is recognition, a thinning atmosphere, a signal from the stars, climate curves bending upward, subatomic anomalies, a virus spreading invisibly. In each case, scientists did what they are trained to do: measure, test, verify. But beneath the methodical process was a deeper realization that our assumptions had limits. That stability can be more fragile than it appears. Science is often portrayed as confident, authoritative. Yet, its true strength lies in confronting uncertainty, in admitting when something doesn't fit, in saying quietly and carefully something is wrong. Those moments are not failures. They are turning points. They force adaptation, cooperation, innovation. They reveal the dynamic nature of the world and our incomplete understanding of it. The unsettling truth is not that problems exist. It's that awareness often arrives gradually, through data no one can ignore. A graph bending upward, a signal repeating, a pattern emerging. And somewhere in a lab, or an observatory, or a research station on the edge of the world, a scientist looks at the numbers and realizes the same thing humanity has realized many times before. We don't know as much as we thought we did. And that realization, more than anything, is what pushes us deeper